As explained in the previous videos, the gas turbine drives the power turbine, which drives the propeller via the reduction gearbox, RGB. The reduction gearbox has two stages. The first stage has helical gears, which gives a larger contact area, enabling the gear to transmit larger forces. The second stage is a spur gear, which includes two small pinion gears and a large bell gear. The gear ratio is 15.4. On engine number 2, there is a propeller brake attached to the left-hand pinion gear. The reduction gearbox drives the AC wide frequency generator and high-pressure oil pump and an overspeed governor. Attached to the gearbox, there's a fuel-cooled oil cooler and an electric auxiliary oil pump. The primary function is to feather the propeller in flight. And finally, we have the propeller pitch actuator, which is controlled by, depending on the engine version, the propeller control unit, PCU, or the propeller valve module, PVM. The lubrication system of the gas turbine is described in part 2 of this video. The lubrication system in the reduction gearbox is simpler. From the fuel-cooled oil cooler, the oil enters a small tank inside the gearbox housing. It has many names: auxiliary tank, which I will use, RGB oil tank, and internal oil cavity. The total capacity, including unusable oil, is 3.68 liters. Oil from the auxiliary tank is used to lubricate the reduction gearbox. Before the oil is collected in a sump, which has a magnetic ship detector. From the sump, the oil passes a filter before it's returned to the main oil tank. The reduction gearbox drives a high-pressure oil pump, which receives oil from the auxiliary oil tank. Only 0.32 liters of the oil in the tank is available for a high-pressure pump, but the supply of oil is continuous when the gas turbine is running. The high-pressure oil pump delivers oil at 1000 psi to the PCU, or the PVM, and to the overspeed governor. The overspeed governor is attached to the high-pressure oil pump casing and acts as a backup in case the normal propeller control fails. Like the high-pressure pump, the overspeed governor sends oil to the PCU, or the PVM. Inside the overspeed governor, there's a flywheel, which rotates with the reduction gearbox. The flywheel acts on a valve, which drains oil to the sump when the rotation speed reaches a specified limitation. Here's a video showing how a governor in a steam engine works. When the engine is running, the weights are pulled out by the centrifugal force, and this controls a valve that regulates the amount of steam that is used to drive the engine. Strictly speaking, centrifugal force doesn't exist, but is the opposite vector of an inwards acceleration caused by the rotational movement that is perceived as a force. A second electrically driven oil pump is used to complement the high-pressure pump. The pump is called the auxiliary pump, or the feathering pump. Most of the oil in the auxiliary tank, 3.22 liters, is exclusively available for the auxiliary pump. This quantity is sufficient to feather the propeller when the gas turbine has stopped. The auxiliary pump runs when the following conditions are met. 1. In flight, when the conditioner is moved to feather position, or during ATPCS sequence. If you wonder about what ATPCS is, please look at part 1 to this video. 2. On ground, during dynamic ATPCS test, or when the fire handle is pulled when the conditioner is set to fuel shuttle position and was in feather position for less than 30 seconds before. This happens when you have to abort and take off and evacuate in a hurry. The auxiliary pump runs automatically for 30 seconds. Afterwards, it needs 10 minutes to cool down. Early ATR variants have a propeller control unit, PCU, with manual propeller control and 4 bladed propellers. In blade governing mode, the conditioner is set between max RPM, which is 100% NP, and minimum RPM, which is 77 NP. The PCU has the following components. 1. Speed-sensitive governor, which is controlled by the conditioner. The governor meters oil from the high-pressure pump to the servo piston. 2. The servo piston, which is connected to the transfer tube. The piston moves back and forth with the oil pressure from the speed-sensitive governor. A ball screw causes the transfer tube to rotate when it's moving forward and aft. The transfer tube receives oil directly from the high-pressure pump. 3. The least selector, which is a valve that opens for the hydraulic line with the least pressure. This is part of the propeller overspeed protection. 4. The beta valve, which is controlled by the power lever when it's behind flight idle. It idles for the power levers to control propeller pitch. 5. The reverse valve, which is controlled by the power lever when it's behind flight idle. When activated, the reverse valve closes the line from the least selector and opens a line from the high pressure pump. This gives the beta valve oil supply at optimum pressure. 6. The feather valve, which opens when the conditioner is set to feather position. 7. The feather solenoid, which opens during ATPCS sequence, and the fire handle is pulled. 8. Low pitch protection and indicating. Low pitch indication is controlled by a switch that is energized when the engine is in fuel governing mode. The transfer tube delivers oil from the servo piston to the pitch change actuator in the propeller hub. The transfer tube is also called beta tube, as the propeller blade pitch angle is often referred to as beta. A low blade angle is called fine pitch, and a high blade angle is called coarse pitch. The pitch change actuator consists of the following components. 1. A servo piston, also called a yoke piston. It can move back and forth. 2. A shank, which is attached offset to the base of each propeller blade. It is inserted in a slot in the servo piston, and when the servo piston moves back and forth, the shank will cause the propeller blade to rotate along its axis. 3. Pitch increased chamber. When oil is directed into this chamber, the servo piston moves aft, causing propeller pitch to increase towards feather position. 4. A pitch decreased chamber. When oil is directed into this chamber, the servo piston moves forward, causing propeller pitch to decrease towards reverse position. 5. A pitch change metering valve. Depending on the forward or aft position of the transfer tube, the pitch change metering valve distributes high pressure oil into one of the chambers. The oil in the other chamber is released and used to lubricate the propeller hub before it's drained to the sump. 6. A pitch lock screw. It rotates with the transfer tube and secures the propeller blades in their current position in case of total loss of oil pressure. This is how the PCU works. In blade governing mode, the high-pressure oil pump sets oil with 1000 psi pressure to the speed-sensitive governor. The conditioner controls the tension of a spring in the governor, which meters the oil pressure to the servo piston, thus regulating NP. The oil is sent to the servo piston via the least selector and the reverse valve, which don't affect the oil pressure. When the conditioner is set to max RPM, the NP will be 100%. When set to the white band, you get 86% NP, and when set to minimum RPM, you get 77% NP. When the propeller tends to turn faster than the desired NP, the speed-sensitive governor will dump some oil to the sump, reducing the oil pressure to the servo piston. This causes the servo piston to direct more oil to the pitch increased chamber. This will increase the load on the propeller and reduce NP. The opposite will happen when the propeller tends to turn slower than the desired NP. In fuel governing mode, the ECU, or the EEC, adjusts fuel flow to maintain 70.8% NP, and the power lever acts on the reverse valve and the beta valve. The reverse valve directs high pressure oil to the beta valve, which meters oil to the servo piston. Moving the power lever forward will reduce the oil pressure to the servo piston, resulting in increased pitch and more forward thrust. Moving the power lever rearward will increase the oil pressure to the servo piston, resulting in reduced pitch and reverse thrust. In fuel governing mode, there's a low pitch light indication. If the overspeed governor registers more than 102.5% NP, the overspeed governor will open the drain valve. This causes the valve in the least selector to switch side. This causes propeller pitch to increase and slow down the propeller. Propeller feathering is achieved by moving the conditioner to feather, which opens the feather valve, and by ATPCS sequence after an engine failure, or by pulling the fire handle, which opens the feather solenoid. I don't have information about how the low-pitch protection works, but I assume that it opens when the servo piston goes beyond the limitation for flight. This will reduce the oil pressure in the transfer tube and reduce the movement of the piston in the pitch change actuator. The synchrophaser is attached to engine number 2 speed-sensitive governor and adjusts engine number 2 NP to match engine number 1 NP and maintain the optimum phase between the propellers in order to minimize the noise. The synchrophaser is inhibited when the power management is set to take off and is otherwise available when NP is over 70%. Maximum authority of the synchrophaser is plus minus 2.5% NP. Late ATR variants have propeller electronic control, PEC, and 6-bladed propellers, which have the benefit of producing less noise. This is achieved by sweeping back the propeller tips, which reduces the load to Mach number, and by having more propeller blades, which reduces the aerodynamic load on each blade. In blade governing mode, the condition level is normally set to auto. Each engine has a propeller interface unit, PIU, which is an electronic box located in the electronic rack behind the cockpit. It has the following functions. 1. When the condition is set to auto, the PIU monitors the position of the power management selector. This determines whether NP shall be 82 or 100%. The PIU sends the signal to the PEC. 2. Processing PEC fault signals. 3. Inhibit propeller anti-icing when NP is 63% or less. The PEC is installed on top of the reduction gearbox and has 2 channels. The channels are self-tested for 3 seconds when the condition level is moved from feather to auto. A failure to one channel will trigger an amber signal channel light, and the other channels automatically takes over. A failure to both channels will result in a PEC fault alert. The propeller valve module, PVM, has the following components. 1. The electro-hydraulic valve, EHV, which is powered and controlled by the PEC. It meters oil to the pitch change actuator and enables normal feathering of the propeller. 2. The protection valve, which is part of the NP overspeed protection, low pitch protection, and backup for feathering. 3. The feather solenoid, which works with the protection valve. 4. The rotary variable differential transducer, RVDT, which transmits the position of the power lever to the PEC. 5. A secondary low pitch stop retraction solenoid. I don't have any information about this one, but I assume it's a kind of backup. If you know the function of this device, please let us know in the comments below. The PEC receives the following information. 1. From the PIU, when the condition lever is set to auto, the position of the power management selector. 2. From the condition lever, when it's set to 100% override or feather, the position of the condition lever. 3. From the EEC, airspeed and altitude. 4. From the electro-hydraulic valve, the pitch of the propeller blades. 5. From the RVDT, the position of the power lever. Based on this information, the PEC computes the pitch changes required to maintain the required NP and send command signals to the electro-hydraulic valve. The 2 hydraulic lines enters the transfer tube, which leads to the pitch change actuator in the propeller hub. I have cheated a little here because I'm using the same drawing as for the engine with the PCU. The main differences are, there is no pitch lock screw, there are 2 hydraulic lines instead of 1 in the transfer tube, and they attach to the pitch change actuator, and they don't rotate. This is how the PVM works. The high pressure oil pump sends oil in 1000 psi pressure to the electro-hydraulic valve, which is powered and controlled by the PEC. Based on signals from the PEC, the electro-hydraulic valve meters oil in 2 hydraulic lines. The first line decreases propeller pitch, or making it finer. I have marked this line with pink color. The other line increases propeller pitch, or making it coarser. I have marked this line with green color. Excessive oil is drained to the sump. In blade governing mode, the PEC calculates the changes in propeller pitch required to maintain the desired NP, and sends commands to the electro-hydraulic valve. When the power management select is set to take off or MCT, NP is 100%, and when the power management select is set to climb or cruise, NP is 82%. When power is increased, or when the speed of the airplane increases, the propeller tends to rotate faster. The PEC will then command the electro-hydraulic valve to meter more oil into the hydraulic line that causes the propeller pitch to increase, and vice versa. In fuel governing mode, the EEC adjusts fuel flow to maintain 70.8% NP, and the power lever controls propeller pitch by regulating oil from the overspeed governor into the pitch change actuator. This figure is simplified and doesn't show the mechanism. Moving the power lever forward will increase the pressure in the hydraulic line that increases propeller pitch. Moving the power lever backward will increase the pressure in the hydraulic line that reduces propeller pitch towards reverse. In fuel governing mode, there's a low pitch light indication. When the PEC is inoperative, the electro-hydraulic valve is no longer powered. In this case, the hydraulic line commanding fine pitch is left open. This causes NP to increase. This is when the overspeed governor and the protection valve come into play. The protection valve is located downstream of the electro-hydraulic valve. The protection valve consists of a movable piston with several valves. During normal operation, the piston is held in position by oil pressure from the overspeed governor, and the oil in the 2 hydraulic lines from the electro-hydraulic valve to pass through the protection valve without interruption. This is called unprotected mode. When NP reaches 102.5%, the overspeed governor starts to dump oil into the drain line. This results in a reduction of the oil pressure to the protection valve. This causes the piston to move, gradually restricting the flow in the 2 lines from the electro-hydraulic valve. When the pressure from the overspeed governor is reduced to 50%, the piston has moved to its full stop, and the supply from the electro-hydraulic valve is blocked. The protection valve will now direct oil into the hydraulic line that increases propeller pitch. This causes NP to decrease, and the overspeed governor slows down, opening up for supply from the electro-hydraulic valve again. And the NP stabilizes at 102.5%. This is called protected mode. Propeller feathering is achieved by moving the condition lever to feather, by ATPC sequence after an engine failure, or by pulling the fire handle. The ATPC sequence is described in part 1 of this video. There are 2 independent feathering systems. The PEC and the electro-hydraulic valve provide the first feather system. The electro-hydraulic valve meters oil into the hydraulic line to increase pitch. The second feather system consists of the feather solenoid, which is open for 30 seconds and acts on the protection valve. When the feather solenoid opens, the oil pressure from the overspeed governor is reduced, and this causes the protection valve to go into protected mode and direct oil from the high pressure pump into the hydraulic line that increases propeller pitch. When the airplane is in flight, the auxiliary pump will run for 30 seconds and assist feathering of the propeller. On ground, the auxiliary pump will run during ATPC's dynamic test, or when the fire handle is activated when the conditioner is in fuel shut-off position and was in feather position for less than 30 seconds before. The transfer tube moves forward and after the pitch change actuator. When the propeller pitch angle moves towards low pitch, the actuator moves forward. At a position corresponding to the lowest blade pitch angle allowed in flight, which is 12.8 degrees, the hydraulic line from the overspeed governor is connected to the drain. This causes the protection valve to go into protected mode and commands propeller pitch to increase. The PEC provides fully automatic synchrophasing between the propellers. It maintains an optimum phase between the propellers, which minimizes the noise.